So here we have a rates of change question, specifically one to do with exponential decay or radioactive decay. And we want to basically show a few things. So here we have the mass, m, of a radioactive isotope is given by the equation m equals m0 e to the negative kt, where m0 is the initial mass and k is a constant, satisfying the equation dm dt equals negative km, negative for the decay. And part 1, if the half-life of the radioactive isotope is capital T, show the relationship, which you should already know. And then the next part, a naturally occurring rock contains two radioisotopes X and Y, and you have two different half-lives, Tx and Ty, where Tx is greater than Ty, because initially the mass of isotope Y is 4 times of X, and show that the rock will contain the same mass of both isotopes at time T equals this expression. So let's quickly get part 1 out of the way, and we'll quickly then move on to part 2. So we are told that it follows the expression m equals m0 e to the negative kt. You are trying to find the half-life. So at T equals capital T, the mass is half of what it was. So let's solve for that. With that in mind, we get half equals e to the negative kt. So log of a half equals negative kt. So log of 2 equals kt. So capital T must equal log 2 over k. Well, that's true, but they wanted us to solve for k. So very similarly, k must equal log 2 over capital T, as expected. Excellent. Now, part 2 tells you you've got two radioisotopes, X and Y. The half-life of radioisotope X and Y are Tx and Ty. So you've got half-life equals Tx, and this is Ty. Initially, so at T equals 0, the mass equals, well, some mass, we don't know, some mass of X, and the mass of this must equal the mass of Y. But what we do know is that the mass of isotope Y is 4 times the mass of isotope X. So we're saying at T equals 0, those are the masses. Well, that means the mass of X, using the formula on the left, must equal, I guess, how should I put this? The mass of X at any point in time should be the mass of X at time 0, which I will call lowercase m for our purposes, because it's a set constant. So I will change my notation a little. So it's the mass of X at time 0, which I'll call 4 lowercase m. So at any point in time, the mass of X is going to be m, representing the starting mass, times e to the negative kt. And the mass of Y would equal m, 4m, e to the negative kt. Now, we can use part 1 now, because part 1 gives us, for a particular half-life t, we know the k. So the k equals log 2 over the half-life, in this case, which is tx, and the k here, which is log 2 over the half-life, which is ty. Now, we don't know what tx and ty are, but we can, subbing our k, that means our mx must equal m e to the negative log 2 over tx times capital T, and my must equal 4m times e to the negative log 2 over ty t. That should be a lowercase t over there. So we now have expressions for mx at any time and my at any time. The question asks us to show the rock will contain the same mass when, basically, we want to solve these simultaneously. We want mx to equal my, and we want to find that t equals 2tx ty over tx minus ty. So that's basically what we'll do. We'll solve these simultaneously. So we'll write them out on the next page again. Now, these are equal. So what you could do is equate them. And quite clearly, the m cancels. That's your first thing. Now, you've got this situation where you've got 4 and you've got exponential and exponential. Now, you can't take the log of both sides. Well, you can, but you can either take the log of both sides. That's one option. Or one option is to move the exponentials to one side. Both are viable. That will be up to you how you want to do it. Perhaps I will take the log of both sides. So if I take the log of the left-hand side, the log of the exponential will just cancel, give me negative log 2 over txt. Now the log on the right-hand side is more complicated, but it's actually not too bad. You just need to think of it as 4 times the exponential, which means you can think of it as log 4 plus log of the exponential using your log laws, and that will then allow you to say that. You would have achieved a very similar outcome if you had just gone straight ahead and did that together. Now, remember what your aim is, right? You know what you're trying to find is t, lowercase. That's your unknown. Your capital Tx and capital Ty are known values, essentially. So just collect like terms and solve for lowercase t. So I'll move that to the other side. So that means you've got log 2 over ty, capital T, minus log 2 over tx, lowercase t, equals log 4. You can take out the t and the log 2. That gives you 1 over ty minus 1 over tx equals log 4. So that means t must equal log 4 over log 2 divided by 1 over ty minus 1 over tx. That's what we're saying it is. So that means I've got log 4 over log 2 divided by tx minus ty over tx, which means I've got log 4 over log 2 multiplied by tx over tx minus ty. Now log 4 over log 2 we can think of as log of 2 all squared. Which is 2 log 2 over log 2. we'll just go back a bit to give us a little bit of space. So we can think of log 4 as log base 2 of 2, log of 2 all squared, which means it's 2 log 2. And given that it's 2 log 2, you can see that the log 2's cancels out. And that gives you 2, giving you an answer of 2 tx ty over tx minus ty. This is our solution to t with a condition that the mass of x is equal to the mass of y. And that's exactly what they're looking for. The time when the two masses are equal is 2 times tx ty all over tx minus ty. And that's how you do the question.